So today we're going to be learning about natural language generation. And this is probably going to be a little different to my previous lectures because this is going to be much more of a kind of survey of lots of cutting-edge research topics that are happening in NLG right now. So before we get to that, we've got a few announcements. So I guess the main announcement is just thank you all so much for your hard work. I know the last week or two have been pretty tough. Assignment 5 was really quite difficult, I think, and it was a challenge to do it in 8 days. So we just really appreciate all the hard work you've put in. We also understand the project proposal was sometimes a bit difficult to understand the expectations for some people. So yeah, these are both new components of the class this year that were not present last year. So, we have to go through some learning curves as well as the teaching staff. So we really want to say thank you so much for putting everything into this class. And please do continue to give us your feedback, both right now and in the end of quarter feedback survey. Okay, so here's the overview for what we're going to be doing today. So today we're going to learn about what's happening in the world of neural approaches for natural language generation. That is a super, super broad title, natural language generation. NLG encompasses a huge variety of research areas, and pretty much each of those could have had their own lectures, and we could have taught a whole quarter's worth of classes on NLG. But we're going to try to cover a selection of things today, and it's mostly going to be guided by the things which I've seen that I think are cool or interesting or exciting. So it's by no means going to be comprehensive, but I hope you're going to enjoy some of the stuff we're going to learn about. Okay, so in particular, we're going to start off by having a recap of what we already know about natural language generation to make sure we're all on the same page. And we're also going to learn a little bit extra about decoding algorithms. So we learned a bit before about greedy decoding and beam search decoding, but today we're going to learn some extra information about that and some other types of decoding algorithms. After that, we're going to go through a pretty quick tour of lots of different NLG tasks and a selection of neural approaches to them. And then after that, we're going to talk about probably the biggest problem in NLG research, which is NLG evaluation and why it is such a tricky situation. And then lastly, we're going to have some concluding thoughts on NLG research, what are the current trends, and where are we going in the future. Okay, so section 1. Let's do a recap. Okay, so natural language generation, to define, it just refers to any setting in which we're generating some kind of text. So for example, NLG is an important subcomponent of lots of different tasks, such as machine translation, we've already met, abstractive summarization, we'll learn a bit more about that later, dialogue, both chit-chat and task-based, also creative writing tasks, such as writing stories and writing poems even. NLG is also a subcomponent of free-form question answering. So I know a lot of you are doing the Squad project right now. That is not an NLG task because you're just extracting the answer from the source document. But there are other question answering tasks that do have a natural language generation component. Image captioning is another example of a task that has an NLG subcomponent. So NLG is a pretty core component of a lot of different NLP tasks. All right, let's go into our recap. So the first thing I want to recap is what is language modeling. I've noticed that some people are a little bit confused about this. I think it might be because the name language modeling sounds like it might mean just simply encoding language, like representing language using embeddings or something. So as a reminder, language modeling has a more precise meaning. Language modeling is the task of predicting the next word given the word so far. So any system which produces this conditional probability distribution that does this task is called a language model. And if that language model system is an RNN, then we often abbreviate it as RNN-language model. Okay, so I hope you remember that. The next thing I'm going to recap is, do you remember what a conditional language model is? The task of conditional language modeling is when you're predicting what word's going to come next, but you're also conditioning on some other input X as well as all of your words so far. So to recap, some examples of conditional language modeling include machine translation, where you're conditioning on the source sentence X. Summarization, you're conditioning on your input text that you're trying to summarize. Dialogue, you're conditioning on your dialogue history, and so on. Okay, next we're going to quickly recap how do you train an RNN language model. I guess it could also be a transformer-based language model or a CNN-based language model, now that you know about those. And it could be conditional or it could be not. So the main thing I want to remind you about is that when you are training this system, then you feed in the target sequence that you're trying to generate. So where it says target sentence from corpus, that's saying that you have some sequence that you're trying to generate, and you feed that into the decoder, the RNN language model, and then it predicts what words are going to come next. So the super important thing is that during training, we're feeding the gold, that is the reference target sentence, into the decoder, regardless of what the decoder is predicting. So even if, let's say, this is a very bad decoder that isn't predicting the correct words, it's not, predicting them high at all, that doesn't matter. We still just input the gold target sequence into the decoder. And I'm emphasizing this because it's going to come up later. This training method is called teacher forcing, which might be a phrase that you've come across elsewhere. So yeah, it refers to the fact that the teacher, that is kind of like the gold input, is forcing the language model to use that on every step instead of using its own predictions on each step. So that's how you train a RNN language model, which might be conditional. Okay, so now recap on decoding algorithms. So you've got your trained language model, which might be conditional. The question is, how do you use it to generate text? So the answer is you need a decoding algorithm. A decoding algorithm is an algorithm you use to generate the text from your trained language model. So in the NMT lecture a few weeks ago, we learned about two different decoding algorithms. We learned about greedy decoding and beam search. So let's quickly recap those. Greedy decoding is a pretty simple algorithm. On each step, you just take what's the most probable word according to the language model. You could say it's the argmax. And then you use that as the next word. You feed it in as the input on the next step. And you just keep going until you produce some kind of end token, or maybe when you reach some maximum length. And I think you're all quite familiar with this because you did it in assignment 5. So yes, this diagram shows how greedy decoding would work to generate this sentence. So as we learned before, due to a kind of lack of backtracking, an inability to go back if you made a wrong choice, the output from greedy decoding is generally pretty poor. Like, it can be ungrammatical, it can be unnatural, kind of nonsensical. Okay, let's recap beam search decoding. So beam search is a search algorithm which aims to find a high probability sequence. So if we're doing translation, that sequence is the sequence of translation words, by tracking multiple possible sequences at once. So the core idea is that on each step of the decoder, you're going to be keeping track of the k most probable partial sequences, which we call hypotheses. And here k is some hyperparameter called the beam size. So the idea is by considering lots of different hypotheses, we're going to try to search effectively for a high probability sequence, but there is no guarantee that this is going to be like the optimal, most high probability sequence. So at the end of beam search, you reach some kind of stopping criterion, which we talked about before, but I won't cover in detail again. And once you've reached your stopping criterion, you choose the sequence with the highest probability, factoring in some adjustments for length, and then that's your output. So just to view this one more time, here's the diagram that we saw in the NMT lecture of beam search decoding once it's completed. And in this scenario, we have a beam size of 2. So this is what it looks like after we've done this exploration problem. This shows the full tree that we explored, and then we've come to some kind of stopping criterion, and we identified the top hypothesis, and that's highlighted in green. So on the subject of beam search decoding, I was watching TV the other day, and I noticed something in Westworld. I think the AI hosts in Westworld maybe used beam search, which is something I wasn't expecting to see on TV. So there's this scene. Westworld is, by the way, a sci-fi series that has these very convincing humanoid AI systems. And there's a scene where one of the AI systems is confronted with the reality of the fact that she, I suppose, is not human, because she sees the generation system of words as she says them. And I was looking at the TV and I thought, is that beam search? Because that diagram looks a lot like this diagram here, but maybe with a bigger beam size. So I thought that was pretty cool, because AI has hit the mainstream when you see beam search on TV. And then if you zoom in really hard, you can see some other exciting words in this screenshot, like knowledge base, forward chaining, and backward chaining. I don't know if that's the same thing as forward prop and backward prop. And also fuzzy logic, algorithms, and neural net. So yeah, beam search, I think, has hit the mainstream now. So if it's good enough for Westworld, maybe it's good enough for us. So with beam search, right, we've talked about how you have this hyperparameter K, or the beam size. And one thing we didn't talk about in the last lecture, so now we're leaving the recap portion, is what's the effect of changing that beam size K? So if you have a really small K, then you're going to have similar problems to greedy decoding. And in fact, if K equals 1, then you are actually just doing greedy decoding. So those same problems are, ungrammatical, maybe unnatural, nonsensical, just kind of plain incorrect output. So what happens if you get larger K? If you have a larger beam size, then you're doing your search algorithm, but considering more hypotheses, right? You're having a larger search space, and you're considering more different possibilities. So if you do that, then we often find that this reduces some of the problems above. So you're much less likely to have this ungrammatical, disjointed output. But there are some downsides to raising K. So, of course, larger K is more computationally expensive, and that can get pretty bad if you're trying to, for example, generate your outputs for a large test set of NMT examples. But more seriously than that, increasing K can introduce some other problems. So, for example, it's been shown that in NMT, increasing the beam size too much actually decreases the BLEU score. And this is kind of counterintuitive, right? Because we were thinking of beam search as this algorithm that tries to find the optimal solution. So surely if you increase K, then you're only going to find a better solution, right? So I think maybe the key here is the difference between optimality in terms of the search problem, that is finding a high probability sequence, and BLEU score, which are two separate things, and there's no guarantee that they actually correspond, right? And I mean, there's a difference again between BLEU score and actual translation quality, as we know. So if you look at the two papers which I've linked to here, which are the ones that show that increasing beam size too much decreases the BLEU score, they explain it by saying that the main reason why this happens is because when you increase the beam size too much, then you end up producing translations that are too short. So, I mean, that kind of explains it to a degree. The translations are too short, therefore they have low BLEU because they're probably missing words that they should contain. But the question is, why does large beam size give you short translations? I think that's harder to answer. When I read these two papers, I didn't see an explicit explanation of why. I think it's part of a larger kind of pattern we see sometimes with beam search, which is when you really increase your search space and make the search much more powerful so that it can consider lots of different alternatives, it can end up finding these high probability sequences which aren't actually the thing that you want. Sure, they're high probability, but they're not actually the thing that you wanted. So another example of that is that in open-ended tasks like, for example, chitchat dialogue, where you're trying to just say something interesting back to your conversational partner, if we use beam search with a large beam size, we find that that can give you some output that is really generic. And I'll give you an example here to show you what I mean. So these are examples from a chitchat dialogue project that I was doing. So here you've got your human chit-chat partner said something like, I mostly eat a fresh and raw diet, so I save on groceries. And then here's what the chatbot said back, depending on the beam size. I'll let you read that. So I would say that this is fairly characteristic of what you see happening when you raise and lower the beam size. When you have a low beam size, it might be more kind of on topic. Like here we can see that eat healthy, I'm a nurse, so I do not eat raw food, and so on. That kind of relates to what the user said. But it's kind of bad English, right? There's some repetition, and it doesn't always make that much sense, right? But then when you raise the beam size, then it kind of converges to a safe, so-called correct response, but it's kind of generic and less relevant, right? It's kind of applicable in all scenarios. What do you do for a living? So the particular data set I was using here is one called Persona Chat that I'll tell you more about later. But it's a chit-chat dialogue data set where each conversational partner has a persona, which is a set of traits. So the reason it keeps talking about being a nurse, I think, is because it was in the persona. But the main point here is that we kind of have an unfortunate trade-off with no Goldilocks zone that's very obvious. I mean, there's kind of an unfortunate trade-off between having kind of bad output, bad English, and just having something very boring. So this is one of the problems that we get with beam search. Okay, so we've talked about greedy decoding and beam search. Yes?
Beam size depending on the position of the sequence you're generating.
The question is, can we have an adaptive beam size dependent on the position that you're in? You mean like in the sequence?
Yeah, where you're generating.
Yeah. I mean, I think I might have heard of a research paper that does that adaptively like raises the capacity of the hypothesis space. It sounds awkward to implement because things fitting into a fixed space in your GPU. But I think that might be possible. I suppose you'd have to learn the criterion on which you increase the beam size. Yeah, seems possible. Okay, so we've talked about beam search and greedy decoding. So here's a new family of decoding algorithms which are pretty simple, sampling-based decoding. So something which I'm calling pure sampling because I didn't know what else to call it. This is just the simple sampling method that says that on each time step of your decoder T, you just want to randomly sample from the probability distribution to obtain your next word. So this is very simple. It's just like greedy decoding, but instead of taking the top words, instead just sample from that distribution. So the reason I called this pure sampling was to differentiate it from top N sampling. And again, this is actually usually called top K sampling, but I already called K the beam size, and I didn't want to be confusing, so I'm going to call it top N sampling for now. So the idea here is also pretty simple. On each step T, you want to randomly sample from your probability distribution, but you're going to restrict to just the top N most probable words. So this is saying that it's like the simple, pure sampling method, but you want to truncate your probability distribution just to be, the top most probable words. So the idea here, kind of like how beam search gave you a hyperparameter to kind of go between greedy decoding and, very exhaustive search. In the same way here, you've got a hyperparameter n, which can take you between greedy search and pure sampling. If you think about this for a moment, if n is 1, then you truncate it to top 1, so you're just taking argmax, which is greedy. And if n is the vocab size, then you don't truncate it at all. You're sampling from everything. That's just the pure sampling method. So here, it should be clear, I hope, if you think a bit, that if you increase n, then you're going to get more diverse and risky output, right? Because you're giving it more to choose from, and you're going lower into the probability distribution, going lower into less likely things. And then if you decrease n, then you're going to get more kind of generic safe output because you're restricting more to the most high probability options. So both of these are more efficient than beam search, which I think is something important to note, because there are no multiple hypotheses to track, right? Because in beam search, on every step T of the decoder, you've got K different, beam size many hypotheses to track. Whereas here, at least if you're only generating one sample, there's only one thing to track. So it's a very simple algorithm. So that is one advantage of these sampling-based algorithms over beam search. Okay, so the last thing I want to tell you that's kind of related to decoding is softmax temperature. So if you recall, on time step T of your decoder, your language model computes some kind of probability distribution, PT, by applying the softmax function to a vector of scores that you got from somewhere, like from your transformer or from your RNN or something. So there's the softmax function again. It's saying that the probability of a word W is this softmax function given the scores. So the idea here of a temperature on the softmax is that you have some kind of temperature hyperparameter tau, and you're going to apply that to this softmax. So all that we're doing is we're dividing all of the scores, or logits you might call them, by the temperature hyperparameter. So again, if you just think about this a little bit, you'll see that raising the temperature, that is increasing the hyperparameter, this is going to make your probability distribution more uniform. And this kind of comes down to the question of like when you multiply all of your scores by a constant, how does that affect the softmax, right? So do things get more far apart or less far apart once you take the exponential? So this is something you can just work out by yourself on paper. But as a kind of a memory shortcut, a good way to think about it is that if you raise the temperature, then the distribution kind of melts and goes soft and mushy and uniform. And if you lower the temperature, like make it cold, then the probability distribution becomes more spiky, right? So like the things which are rated as high probability become like even more disproportionately high probability compared to the other things. I think that's the easier way to remember it. Today I had to work it out on paper, and then I realized that just the temperature visualization thing usually gets me there quicker. So one thing I want to note is that softmax temperature is not a decoding algorithm. I know that I put it in the decoding algorithm section. That was just because it's kind of a thing, a simple thing that you can do at test time to change how decoding happens, right? You don't need to train with the softmax temperature. So it's not a decoding algorithm itself. It's a technique that you can apply at test time in conjunction with a decoding algorithm. So for example, if you're doing beam search or you're doing some kind of sampling, then you can also apply a softmax temperature to change, this kind of risky versus safe trade-off. Any questions on this? Okay, so here's a summary of what we just learned about decoding algorithms. Greedy decoding is a simple method. It gives kind of low quality output in comparison to the others, at least beam search. Beam search, especially when you've got a high beam size, it searches through lots of different hypotheses for a high probability output. And this generally is going to deliver better quality than greedy search. But if the beam size is too high, then you can have these kind of counterintuitive problems we talked about before, where you've retrieved some kind of high probability but unsuitable output. So something that's too generic or something that's too short. And we're going to talk about that more later. Sampling methods are a way to get more diversity via randomness. Randomness might be your goal in itself. So this is good if you want to have some kind of, for example, open-ended or creative generation setting, like generating poetry or stories. Then sampling is probably a better idea than beam search because you want to have a kind of source of randomness to write different things creatively. And top-end sampling allows you to control the diversity by changing n. And then lastly, softmax temperature is another way to control diversity. So there's quite a few different knobs you can turn here. And it's not a decoding algorithm, it's just a technique that you can apply alongside any decoding algorithm. Although it wouldn't make sense to apply it with greedy decoding, because even if you make it more spiky or more flat, the argmax is still the argmax, so it doesn't make sense. Okay, cool. Well, I'm going to move on to section 2. So section 2 is NLG tasks and neural approaches to them. As mentioned before, this is not going to be an overview of all of NLG. That would be quite impossible. This is going to be some selected highlights. So in particular, I'm going to start off with a fairly deep dive into a particular NLG task that I'm a bit more familiar with, and that is summarization. So let's start off with a task definition for summarization. One sensible definition would be, given some kind of input text X, you want to write a summary Y, which is shorter than X and contains the main information of X. So summarization can be single document or multi-document. Single document means that you just have a summary Y of a single document X. In a multi-document summarization, you're saying that you want to write a single summary Y of multiple documents, X1 up to Xn. And here, typically, X1 and up to Xn will have some kind of overlapping content. So for example, they might all be different news articles from different newspapers about the same event, right? Because it kind of makes sense to write a single summary that draws from all of those. It makes less sense to summarize things that are about different topics. There is further subdivision of task definitions in summarization. So I'm going to describe it via some data sets. Here are some different really common data sets, especially in neural summarization, and they kind of correspond to different lengths and different styles of text. So a common one is the gigaword dataset, and the task here is that you want to map from the first 1 or 2 sentences of a news article to write the headline. And you could think of this as sentence compression, especially if it's kind of one sentence to headline, because you're going from a longish sentence to a shortish headline style sentence. Next one that I wanted to tell you about is this. It's a Chinese summarization dataset, but I see people using it a lot. And it's from a microblogging website where people write summaries of their posts. So the actual summarization task is you've got some paragraph of text, and then you want to summarize that into, I think, a single sentence summary. Another one, two actually, are the New York Times and CNN Daily Mail data sets. So these ones are both of the form, you've got a whole news article, which is actually pretty long, like hundreds of words, and then you want to summarize that into like maybe a single sentence or multi-sentence summary. The New York Times ones are written by, I think, librarians or people who write summaries for library purposes. And then one I just spotted today when I was writing this list is there's a new, fairly new, like last 6 months data set from WikiHow. So from what I can tell, this seems to be, you've got a full how-to article from WikiHow, and then you want to boil this down to the summary sentences, which are kind of cleverly extracted from throughout the WikiHow article. They're kind of like headings. So I looked at this paper and it seems that this is kind of interesting because it's a different type of text. As you might have noticed, most of the other ones are news-based, and this is not, so that kind of poses different challenges. Another kind of division of summarization is sentence simplification. So this is a related but actually different task. In summarization, you want to write something which is shorter and contains the main information, but is still maybe written in just as complex language. Whereas in sentence simplification, you want to rewrite the source text using simpler language, right? So like simpler word choices and simpler sentence structure. That might mean it's shorter, but not necessarily. So for example, simple Wikipedia is a standard data set for this. And the idea is you've got standard Wikipedia and you've got a simple Wikipedia version, and they mostly align up. So you want to map from some sentence in one to the equivalent sentence in the other. Another source of data for this is Newsella, which is a website that rewrites news for children, actually at different learning levels, I think. So you have multiple options for how much it's simplified. Okay, so that's the definition, or the many definitions of summarization as different tasks. So now I'm going to give an overview of like what are the main techniques for doing summarization. So there's two main strategies for summarization. You can call them extractive summarization and abstractive summarization. And the main idea, as I hinted at earlier, is that in extractive summarization, you're just selecting parts of the original text to form a summary. And often this will be whole sentences, but maybe it will be more granular than that, maybe phrases or words. Whereas abstractive summarization, you're going to be generating some new text using NLG techniques. So the idea is that it's generation from scratch. And my visual metaphor for this is it's kind of like the difference between highlighting the parts with a highlighter or writing the summary yourself with a pen. I think the high-level things to know about these two techniques are that extractive summarization is basically easier, at least to make a decent system to start, because selecting things is probably easier than writing text from scratch. But extractive summarization is pretty restrictive, right? Because you can't really paraphrase anything, you can't really do any powerful sentence compression if you can only just select sentences. And of course, abstractive summarization as a paradigm is more flexible, and it's more how humans might summarize, but as noted, it's pretty difficult. So I'm going to give you a very quick view of what pre-neural summarization looked like. And here we've got, this is a diagram from the speech and language processing book. So pre-neural summarization systems were mostly extractive. And like pre-neural NMT, which we learned about in the NMT lecture, it typically had a pipeline, which is what this picture is showing. So a typical pipeline might have three parts. First, you have content selection, which is essentially choosing some of the sentences from the source document to include. And then secondly, you're going to do some kind of information ordering, which means choosing what order should I put these sentences in. And this is particularly a more non-trivial question if you were doing multiple document summarization, because your sentences might come from different documents. And then lastly, you're going to do your sentence realization. That is actually turning your selected sentences into your actual summary. So although we're not doing kind of free-form text generation, there might be some kind of editing, for example, like simplifying editing or removing parts that are redundant or fixing continuity issues. So for example, you can't refer to a person as she if you never introduced them in the first place. So maybe you need to change that she to the name of the person. So in particular, these pre-neural summarization systems had some pretty sophisticated algorithms for content selection. So, for example, you would have some sentence scoring functions. This is a more simple way you might do it, is you might score all of the sentences individually, and you could score them based on features such as, are there, topic keywords in the sentence? If so, maybe it's an important sentence that we should include. And you could compute those keywords using statistics such as, TF-IDF, for example. You could also use pretty basic but powerful features such as where does this sentence appear in the document? If it's near the top of the document, then it's more likely to be important. There were also some more complex content selection algorithms, such as, for example, there are these graph-based algorithms which kind of view the document as a set of sentences, and those sentences are the nodes of the graph. And you imagine that all sentence pairs have an edge between them, and the weight of the edge is kind of how similar the sentences are. So then if you think about the graph in that sense, then now you can try to identify which sentences are important by finding which sentences are central in the graph. So you can apply some kind of general purpose graph algorithms to figure out which nodes are central, and this is a way to find central sentences. Okay, so back to summarization as a task. I can't remember if we talked about Rouge already. We've certainly talked about Blue. But I'm going to tell you about Rouge now, which is the main automatic metric for summarization. So Rouge stands for Recall-Oriented Understudy for Gisting Evaluation. I'm not sure if that was the first thing they came up with or if they made it like that to match Blue. Here's the equation for, well, I suppose one of the Rouge metrics. I'll tell you more about what that means later. And you can read more in the original paper, which is linked to the bottom. So the overall idea is that Rouge is actually pretty similar to Blue. It's based on n-gram overlap. So some main differences with Blue are Rouge doesn't have a brevity penalty. I'll talk more about that in a minute. The other big one is that Rouge is based on recall, while Blue is based on precision. So you can see it's there in the title. So if you think about this a little bit, I think you can say arguably precision is more important for machine translation. That is, you only want to generate text that appears in one of your reference translations. And then to avoid taking a really conservative strategy where you only generate really safe things in a really short translation, that's why you add the brevity penalty to make sure that it tries to write something long enough. And then by contrast, recall is more important for summarization because you want to include all the information, the important information in your summary. Right, so the information that's in the reference summary is assumed to be the important information, so recall means that you captured all of that. And then I suppose if you assume that you have a maximum length constraint for your summarization system, then those two kind of give a trade-off, right, where you want to include all the information, but you can't be too long as a summary. So I think that's the kind of justification why you have recall and precision for these two different tasks. However, confusingly, often an F1, that is combination of precision and recall version of Rouge, is reported anyway in the summarization literature. And to be honest, I'm not entirely sure why this is. Maybe it's because of the lack of explicit max length constraint. Anyway, I tried to search for that, but I couldn't find an answer. So here's some more information on Rouge. If you remember, Blue is reported as a single number, right? Blue is just a single number, and it is a combination of the precisions for the different n-grams, which is usually 1 to 4. Whereas Rouge scores are usually reported separately for each n-gram. So the most commonly reported Rouge scores are Rouge 1, Rouge 2, and Rouge L. So Rouge 1, not to be confused with Rogue One, a Star Wars story. I feel like since that film came out, I see so many people mistyping this, and I think it's related. So Rouge 1 is based on unigram overlap, and Rouge 2 based on bigram overlap. It's kind of an analogy to Blue, really, except recall-based, not precision-based. The more interesting one is Rouge L, which is longest common subsequence overlap. So the idea here is that you're interested not only in particular n-grams matching up, but in how long a sequence of words can you find that appear in both. So you can read more about these metrics in the paper that was linked on the previous page. And another really important thing to note is there's now a convenient Python implementation of Rouge. And maybe it is not apparent why that's exciting, but it's actually pretty exciting because for a long time there was just this Perl script that was quite hard to run and quite hard to set up and understand. So someone out there has been a hero and has implemented a pure Python version of Rouge and checked that it really does match up to the Perl script that people were using before. So if any of you are using Rouge or doing summarization for your projects, make sure that you go use that because it will probably save you some time. Okay, so we're going to return to Rouge a little bit later. I know that in assignment 4, you thought about the shortcomings of blue as a metric, and for sure Rouge has some shortcomings as well as a metric for summarization, and we're going to come back to that later. Okay, so we're going to move on to neural approaches for summarization. Going back to 2015, I don't have another dramatic reenactment, I'm afraid. Rush et al. Published the first seek-to-seek summarization paper. So they were viewing this as, NMT has recently been super successful. Why don't we view abstractive summarization as a translation task and therefore apply standard translation seek-to-seek methods to it? So that's exactly what they did. And they applied a standard attention model, and then they did a pretty good job at gigaword summarization. That's the one where you're converting from the first sentence of the news article to the headline. So it's kind of like sentence compression. So crucially, this is kind of the same order of magnitude of length as NMT, right? Because NMT is sentence to sentence, and this is kind of sentence to sentence, maybe at most 2 sentence to sentence. So this works pretty well, and you can get pretty decent headline generation or sentence compression using this kind of method. Okay, so after that, since 2015, there have been lots more developments in neural abstractive summarization. And you can kind of group together these developments in a collection of themes. So one theme is make it easier to copy. This seems pretty obvious because in summarization, you're going to want to copy over quite a few words and even phrases. But don't copy too much. That's the other thing, is that if you make it too easy to copy, then you copy too much. So then there's other research showing how to prevent too much copying. The next thing is some kind of hierarchical or multi-level attention. So as I just showed, the attention has been pretty key to abstractive neural summarization so far. So there's been some work looking at, can we kind of make this attention work at a more kind of high-level, low-level, coarse, fine version, so that we can kind of maybe do our selection at a higher level and at a lower level. Another thing which is kind of related is having some more kind of global content selection. So if you remember when we were talking about the pipelined pre-neural summarization, they had these different content selection algorithms. And I think you can say that kind of naive attention seek-to-seek is not necessarily the best way to do content selection for summarization. Maybe you want a more kind of global strategy where you choose what's important. It's not so apparent here when you're doing this small-scale summarization, but if you imagine that you're summarizing a whole news article and you're choosing which information, kind of deciding on each decoder step what to choose doesn't seem like the most global strategy. What else have we got? There's using reinforcement learning to directly maximize Rouge or other discrete goals you might care about, such as maybe the length of the summary. And I say discrete here because Rouge is a non-differentiable function of your generated outputs. There's no easy way to differentiably learn that during training in the usual way. My last point on this list is the kind of theme of resurrecting pre-neural ideas, such as those graph algorithms that I mentioned earlier, and working them into these new seek-to-seek abstractive neural systems. And I'm sure there's more as well. So I'm going to show you a few of these, especially because even if you're not particularly interested in summarization, a lot of the ideas that we're going to explore here are actually kind of applicable to other areas of NLG or just other areas of NLP deep learning. So the first thing on the list is making it easier to copy, which seems like probably the first thing you want to fix if you've just got basic seek-to-seek with attention. So a copying mechanism, which can exist outside of summarization. The reason why you want this is that basic seek-to-seek with attention, they're good at writing fluent output, as we know, but they're pretty bad at copying over details like rare words correctly. So a copy mechanism is just the kind of sensible idea of saying, let's have an explicit mechanism to just copy over words. So for example, you could use the attention distribution to kind of select what you're going to copy. So if you're allowing both copying over words and generating words in the usual way with your language model, then now you've got a kind of hybrid extractive abstractive approach to summarization. So there are several papers which propose some kind of copy mechanism variants. And I think the reason why there's multiple is because there's kind of a few different choices you can make about how to implement this. And that means that there's a few different versions of how to implement a copy mechanism. So yeah, there's several papers here which you can look at. I'm going to show you a diagram from a paper that I did a few years ago with Chris. So this is just one example of how you can do a copying mechanism. So the way we did it is we said that on each decoder step, you're going to calculate this probability pgen, and that's the probability of generating the next word rather than copying it. And the idea is that this is computed based on your current kind of context, your current decoder hidden state. So then once you've done that, then the idea is you've got your attention distribution as normal, and you've got your kind of output, generation distribution as normal, and you're going to use this pgen, which is just a scalar. You're going to use that to kind of mix together these two probability distributions. So what this equation is telling you is it's saying that the final output distribution for what word's going to come next, it's kind of saying, it's the probability of generating times your probability distribution of what you would generate, but then also the probability of copying, and then also what you're attending to at that time. So the main thing is you're using attention as your copying mechanism. So attention is kind of doing double duty here. It's both being useful for the generator to maybe choose to rephrase things, but it's also being useful as a copying mechanism. And I think that's one of the several things that these different papers do differently. I think I've seen a paper that maybe has like two separate attention distributions, one for the copying and one for the attending. Other choices you can make differently are, for example, do you want pgen to be this kind of soft thing that's between 0 and 1, or do you want it to be a hard thing that has to be either 0 or 1? You can also make decisions about, like, do you want the pgen to have supervision during training? Do you want to kind of annotate your data set saying these things are copied, these things are not? Or do you want to just like learn it end to end? So there's multiple ways you can do this, and this has now become pretty standard. Okay, so copy mechanism seems like a sensible idea, but there's a big problem with them, which is what I mentioned earlier, and that problem is that they copy too much. So when you run these kinds of systems on summarization, you find that they end up copying a lot of long phrases and sometimes even whole sentences. And unfortunately, your dream of having an abstractive summarization system isn't going to work out because your copy augmented seek system has just collapsed into a mostly extractive system, which is unfortunate. Another problem with these copy mechanism models is that they are bad at overall content selection, especially if the input document is long. And this is what I was hinting at earlier. Let's suppose that you are summarizing something that's quite long, like a news article that's hundreds of words long, and you want to write a several sentence summary. It doesn't seem like the kind of smartest choice to, on every step of writing your several sentence summary, be choosing again what to attend to, what to select, what to summarize. It seems better to kind of make a global decision at the beginning and then summarize. So yeah, the problem is there's no overall strategy for selecting the content. So here's a paper that I found. Nope, not yet. Okay, so how might you do better content selection for neural summarization? So if you remember, in this pre-neural summarization we looked at, you had completely separate stages in the pipeline, right? You had a content selection stage and you had a surface realization, that is the text generation stage. But in our seek attention systems, these two stages are just completely mixed together, right? You're doing your step-by-step surface realization, that is text generation, and then on each of those you're also doing content selection. So, yep, this doesn't make sense. So I found a paper which is published, I think, last year, which gives a quite nice kind of simple solution to this problem. And it's called bottom-up summarization. So in this paper, if you look at the figure, the main idea is pretty simple. It says that first you're going to have a content selection stage, and this is just thought of as a neural sequence tagging model problem, right? You run through your source document and you kind of tag every word as include or don't include. So you're just kind of deciding like what seems important, what seems like it should make it into the summary, and what doesn't. And then the bottom-up attention stage says that now your seek with attention system, which is going to generate the summary, you're going to kind of apply a mask, apply a hard constraint that says that you can't attend to words that were tagged don't include. So this turns out to be pretty simple but effective. Because it's a better overall content selection strategy, because by doing this first content selection stage via sequence tagging, you're kind of just doing the selection thing without also at the same time doing the generation thing, which I think turns out to be a better way to make better decisions about what to include. And then separately, this also means, as a great side effect, you have less copying of long sequences in the generation model. Because if you're not allowed to attend to things which you shouldn't be including, then it's kind of hard to copy a really long sequence, right? Like if you want to copy a whole sentence, but the sentence has plenty of don't include words in it, then you can't really copy a long sequence. You have to break it up. So what the model ends up doing is it kind of has to skip around to the parts it's meant to include, and then it's forced to be more abstractive to put the parts together. Yep.
How do they backpropagate through that masking decision?
The question is, during training, how do they backpropagate through the masking decision? Yeah, I think it might be trained separately. I'm not sure, you can go check the paper. I've read a lot of papers in the last day, so I can't quite remember. I think it might be trained separately, but they might have tried training it together, but it didn't work as well. I'm not sure, you can check it out. Okay, so another paper I wanted to tell you about is a paper which used reinforcement learning to directly maximize Rouge for neural summarization. So this was a paper from 2 years ago, and the main idea is they're going to use RL to directly optimize, in this case, Rouge-L, the metric. So by contrast, the standard maximum likelihood training, that is the training objective we've been talking about for the whole class so far for language models, that can't directly optimize Rouge-L because it's a non-differentiable function. So they use this RL technique to compute the Rouge score during training, and then use reinforcement learning to backprop to the model. So the interesting finding from this paper is that if they just use the RL objective, then they do indeed get higher Rouge scores. So they can successfully optimize this Rouge-L metric that they were aiming to optimize. But the problem is that when you do that, you get lower human judgment scores. So on the right, we're seeing that the RL-only model has actually pretty bad readability and relevance human judgment scores. It's worse than just the maximum likelihood supervised training system. So this is a quote from their blog post. They said, "We observed that our models with the highest Rouge scores also generated barely readable summaries." So this is I suppose, a problem, right? If you try to directly optimize for the metric, then you might start finding that you're kind of gaming the metric and not optimizing for the true task, right? Because we know, just as we knew that blue was not a perfect analogy to actual translation quality, so is Rouge not a perfect analogy to summarization quality. But they did do something cool, which is they found that if you combine the two objectives, so the kind of, predict the language model sequence objective, and then also like produce an overall summary that gets a high Rouge score objective, and you combine them together, then you can get a better human judgment scores, which in the end is the closest thing we have to a measure of actual summarization quality. Okay, so I'm going to move on to dialogue, which is a different NLG kind of family of tasks. So really, dialogue encompasses a really large variety of settings, and we're not going to cover them all, but here's a kind of overview of all the different kinds of tasks that people might mean when they say dialogue. So there's task-oriented dialogue, and this kind of refers to any setting where you're trying to kind of get something done in the conversation. So for example, you've got kind of assistive tasks where it's assumed that you have, maybe the dialogue agent is trying to help a human user do something, like maybe giving customer service or recommendations, answering questions, helping the user, accomplish a task like buying or booking something. These are the kinds of tasks which the virtual assistant on your phone can do or can kind of do. Another family of task-oriented dialogue tasks are cooperative tasks. So this is kind of anything where you've got two agents who are trying to solve a task together via dialogue. And the opposite of that would be adversarial. So anything where you have two agents who are trying to compete in a task, and that competition is conducted through dialogue. So the opposite to task-oriented dialogue is social dialogue. So that's something where there is no explicit task other than to, I suppose, socialize. So chitchat dialogue is just dialogue where you're just doing it for social fun or for company. I've also seen some work on kind of like therapy or mental well-being dialogue. I'm not sure if this should go in task or social, it's kind of a mix, but I suppose these are ones where the goal is to maybe offer kind of emotional support to the human user. So as a very kind of brief overview of how the deep learning renaissance has kind of changed dialogue research, I think you could say that kind of pre-deep learning, the difficulty of open-ended, free-form natural language generation meant that dialogue systems were often not doing free-form NLG. They might use predefined templates, meaning that you have a template where you just fill in some slots with the content, or maybe you retrieve an appropriate response from a corpus of responses that you have in order to find, an appropriate response for the user. And these are by no means simple systems. They had some very complex things going on, like deciding, what the dialogue state is and what template you should use and so on, and all the natural language understanding components of understanding the context so far. But one effect that deep learning had is that since, again, kind of 2015, which is when NMT became standard, there's been, just like summarization, lots of papers applying seek-to-seek methods to dialogue. And this has kind of led to a renewed interest in open-ended, free-form dialogue systems. So if you want to have a look at what did those early seek-to-seek dialogue papers look like, here's two kind of early ones, like maybe the first ones to apply seek-to-seek. Okay, so people quickly applied seek-to-seek NMT methods to dialogue, but it quickly became very apparent that this kind of naive application of standard NMT methods has some serious pervasive deficiencies when applied to a task like chitchat dialogue. And this is even more true than it was for summarization. So what are some examples of these serious pervasive deficiencies? One would be genericness or boring responses, and I'll go into more detail about these in a moment. Another one is irrelevant responses. So that's when the dialogue agent kind of says something back that's just kind of unrelated to what the user said. Another one is repetition. This is pretty basic, but it happens a lot. So that's also repetition within the utterance and maybe repetition across utterances. Another difficulty is kind of lack of context, like not remembering the conversation history. Obviously, if you do not condition on the whole conversation history, there's no way your dialogue agent can use it, but it is a challenge, especially if you have a very long dialogue history, to figure out how to condition on it effectively. Another problem is a lack of consistent persona. So if you kind of naively, as in maybe those two papers that I referenced on the previous slide, if you naively train a kind of standard seek-to-seek model to maybe take the the user's last utterance and then say something back, or maybe even the whole dialogue history and say something back, often your dialogue agent will have this completely inconsistent persona. Like one moment it will say that it lives in Europe, and then it will say lives in, I don't know, China or something, and it just doesn't make sense. So I'm going to go through some of these problems and give you a bit more detail on them. So first, this irrelevant response problem. So in a bit more detail, your problem is that seek-to-seek is often generating some response that's kind of unrelated to the user's utterance. So it can be unrelated because it's simply generic, which means that this is kind of like an overlap with the generic response problem, or it can be kind of unrelated because the model's choosing to kind of change the subject to something unrelated. So one solution of many, there are a lot of different papers which kind of attack this irrelevant response problem, but just one for example, is that you should change the training objective. So instead of trying to optimize mapping from input S to response T, such that you're maximizing the conditional probability of T given S, instead you should maximize the maximum mutual information. So that's what this is here. So maximum mutual information, you can kind of rewrite the objective like this. And if you want to see some more detail, you can go look at this paper here. But the idea is that you're trying to find your response T that kind of maximizes this thing, which is kind of like saying it needs to be probable given the input, but kind of like as a ratio of its probability in itself. So if T is very high likelihood, then it gets penalized. And it's kind of like about the ratio of the probability given the input and just the standalone probability. So the idea is that this is meant to discourage just saying generic things that just have a high PT by themselves. So that's the irrelevant response problem. And as I just hinted at, there's definitely a strong link between the irrelevant response problem and the kind of generic or boring response problem. So to look at the genericness or boring response problem. So I think there are some pretty easy fixes that you can make to a degree, ameliorate the boring response problem. Whether you're really getting to the heart of the issue is a different question. But some kind of easy test time fixes that you can certainly do are, for example, you can just directly upweight rare words during beam search. So you can say all rare words kind of get a boost to their log probabilities, and then now we're more likely to produce them during beam search. Another thing you could do is you could use, for example, a sampling decoding algorithm rather than beam search, and we talked about that earlier. Or you could use, softmax temperature as well. That's another thing. So those are kind of test time fixes, and you could regard those as a kind of late intervention, right? So an earlier intervention would be maybe training your model differently. So I'm calling these kind of conditioning fixes because these fixes kind of relate to conditioning your model on something that's going to help it be less boring. So one example is maybe you should condition the decoder on some kind of additional context. So for example, there's some work showing that, if you're doing chit-chat dialogue, then maybe you should go and sample some related words that are related to what the user said, and then just kind of attend to them when you generate. And then you're more likely to say something that's kind of contentful and interesting compared to the boring things you were saying before. Another option is you could train a retrieve and refine model rather than a generate from scratch model. So by retrieve and refine, I mean you suppose that you have some kind of corpus of just general kind of utterances, things that you could say, and then maybe you sample one from that test set or the training set, and then you edit it to fit the current situation. So it turns out that this is a pretty strong method to produce much more kind of diverse and human-like and interesting utterances, because you can get all of that kind of fine-grained detail from the sampled utterance, and then you edit it as necessary to fit your current situation. So, I mean, there are downsides of these kinds of methods, like maybe it can be hard to edit it to actually appropriately fit the situation, but it's certainly a way to effectively get like some more diversity and interest in that. So on the subject of the repetition problem, that was another kind of major problem we noted for applying seek-to-seek to chitchat. Again, there are kind of simple solutions and more complex solutions. So a simple solution is you could just block repeating n-grams during beam search. And this is usually really quite effective. And what I mean by that is during beam search, when you're kind of considering, what are my k hypotheses, which is just kind of the top k in the probability distribution, you say, well, anything that would constitute a repeating n-gram just gets thrown out. So when I say constitute a repeating n-gram, I mean, if you did take that word, would you now be creating a repeating, let's say, 2-gram? Bigram, and if we're deciding that we're banning all repeating bigrams or trigrams or whatever, then you essentially just have to check for every possible word that you might be looking at in beam search whether that would create a repeating n-gram. So this works pretty well. I mean, it's by no means a kind of principled solution, right? It feels like we should kind of have a better way to learn not to repeat, but as a kind of effective hack, I think that works pretty well. So some more complex solutions are, for example, you can train something called a coverage mechanism. So in seek-to-seek, and this is mostly inspired by the machine translation setting, a coverage mechanism is a kind of objective that prevents the attention mechanism from attending to the same words multiple times or too many times. And the intuition here is that maybe repetition is caused by repeated attention. So if you attend to the same things many times, then maybe you're going to repeat the same output many times. So if you prevent the repeated attention, you prevent the repeated output. So this does work pretty well, but it's definitely more of a complex thing to implement. It's less convenient. And I don't know, in some settings it does seem like the simple solution is easier and works just as well. So other complex solutions might be you could define a training objective to discourage repetition. You could try to define something differentiable, but one of the difficulties there is that because you're training with teacher forcing, right, where you're always like looking at the gold input so far, then you never really do the thing where you generate your own output and start repeating yourself. So it's kind of hard to define the penalty in that situation. So maybe this needs to be a kind of non-differentiable function. So kind of like how the Paulus et al. Paper was optimizing for rouge, maybe we kind of optimize for not repeating, which is a discrete function of the input. I'm going to skip ahead to storytelling. So in storytelling, there's a lot of interesting neural storytelling work going on right now. And most of it uses some kind of prompt to write a story. So for example, writing a story given an image or given a writing prompt, or writing the next sentence of a story given the story so far. So here's an example of generating a story from an image. And what's interesting here is that we have this image, which is a picture of, I don't know, what appears to be an explosion. And then here you have a story about the image, but written in the style of Taylor Swift lyrics. So it says, "You have to be the only light bulb in the night sky. I thought, oh God, it's so dark out of me that I missed you, I promise." And what's interesting here is there wasn't any straightforward supervised, image captioning data set of, explosions and Taylor Swift lyrics. They kind of learned this separately. So how they did this is that they used a kind of common sentence encoding space. So they used this particular kind of sentence encoding called skip thought vectors. And then they trained this COCO image captioning system to go from the image to the encoding of the sentence. And then separately, they also trained a language model, a conditional language model, to go from the sentence encoding to the Taylor Swift lyrics. And then because you had this shared encoding space, you can now put the two together and then go from the picture to the embedding to the Taylor Swift style output, which I think is pretty amazing. Wow, I've really lost track of the time, so I think I have to hurry up quite a lot. So we've got some really impressive story generation systems recently. And this is an example of a system which proposed a new data set where you write a story given a prompt. And they made this very impressive, very beefed up convolutional language model, seek-to-seek system, that generates the story given the input. And I'm not going to go through all these details, but I encourage you, if you want to check out what's the state of the art in story generation, you should check this out. There's a lot of different interesting things going on with very fancy attention and convolutions and so on. And they managed to generate some really interesting, impressive stories. So here, if you look at this example, we've got some really interesting kind of story generation that's kind of diverse, it's non-generic, it's stylistically dramatic, which is good, and it's related to the prompt. But I think you can see here kind of the limits of what this state-of-the-art story generation system can do, which is that although it's kind of in style, it's mostly kind of atmospheric and descriptive. It's not really moving the plot forward. There's no kind of events here, right? So the problem is this gets even worse when you generate for longer. When you generate a long text, then it will mostly just stay on the same idea without moving forward with new ideas. Okay, so I'm going to skip forward a lot and sorry not to have planned better. There's a lot of information in here which you want to check out about poetry generation and other things. I'm going to skip ahead because I want to get to the NLG evaluation section because that's pretty important. So we've talked about automatic evaluation metrics for NLG. And we know that these word overlap-based metrics, such as BLUE and Rouge and Meteor, we know they're not ideal for machine translation. They're kind of even worse for summarization, mostly because summarization is even more open-ended than machine translation. And that means that having this kind of rigid notion of you've got to match the n-grams is even less suitable. And then for something even more open-ended like dialogue, then it's just kind of a disaster. It's not even a metric that gives you a good signal at all. And this also applies for anything else open-ended like story generation. So it's been shown, and you can check out the paper at the bottom, that word overlap metrics are just not a good fit for dialogue. So the orange box is showing you some plots of the correlation between human score on a dialogue task and BLUE 2, some variation of BLUE. And the problem here is that you're not seeing much of a correlation at all, right? It seems that particularly on this dialogue setting, the correlation between the BLUE metric and the human judgment of whether it's a good dialogue response is, the correlation is, I mean, it looks kind of non-existent. It's at least very weak. So that's pretty unfortunate, and there's some other papers that show much the same thing. So you might think, well, what other automatic metrics can we use? What about perplexity? So perplexity certainly captures how powerful your language model is, but it doesn't tell you anything about generation. So for example, if your decoding algorithm is bad in some way, then perplexity is not going to tell you anything about that, right? Because decoding is something you apply to your trained language model. Perplexity can tell you you've got a strong language model or not, but it's not going to tell you necessarily how good your generation is. So some other thoughts you might have about automatic evaluation are, well, what about word embedding-based metrics? So the main idea with word embedding-based metrics are you want to compute the similarity of the word embeddings, or maybe of the average of the word embeddings across the sentence, not just the overlap of the words themselves. So the idea is that rather than just being very strict and saying only the exact same word counts, you say, well, if the words are similar in word embedding space, then they count. So this is certainly more flexible, but unfortunately, the same paper I showed before shows that this doesn't correlate well either with human judgments of quality, at least for the dialogue task they're looking at. So here the middle column is showing the correlation between human judgment and some kind of average of word embedding based metric. So yeah, that doesn't look great either, not a great correlation. So if we have no automatic metrics to adequately capture overall quality for natural language generation, what can we do instead? So I think often the strategy is that you end up defining some more kind of focused automatic metrics to capture the particular aspects of the generated text that you might be interested in. So for example, you might be interested in fluency, and you could compute that by just kind of running a well-trained language model over your text and generating the probability. And that's kind of a proxy for how well it's written, good, fluent grammatical text. If you're particularly interested in maybe generating text in a particular style, then you could take a language model that's trained on the corpus representing that style, and now the probability tells you not only is it good text, but is it in the right style. There are some other things as well there, like diversity, and you can count that pretty easily by just having some statistics about how much you're using rare words. Relevance to input, you could kind of compute a similarity score with the input. And there are just some simple things like length and repetition that you surely can count. And yes, it doesn't tell you the overall quality, but these things are worth measuring. So I think my main point is that, yes, we have a really difficult situation with NLG evaluation. There's no kind of overall metric often that captures overall quality. But if you measure lots of these things, then they certainly can help you track some important things that you should know. So we've talked about how automatic evaluation metrics for NLG are really tough. So let's talk about human evaluation. Human judgments are regarded as the gold standard, right? But we already know that human evaluation is slow and expensive. But are those the only problems with human eval? Let's suppose that you do have access to, let's say, the time or money you need to do human evaluations. Does that solve all of your problems? Suppose you have unlimited human eval, does that actually solve your problems? And my answer is no. And this is kind of from personal experience. Conducting human evaluation in itself is very difficult to get right. It's not easy at all. And this is partially because humans do a lot of weird things. Humans are, unlike a metric, are an automatic metric. They're inconsistent. They can be illogical. Sometimes they just get bored of your task and they don't really pay attention anymore. They can misinterpret the question you asked. And sometimes they do things and they can't really explain why they did it. So as a kind of case study of this, I'm going to tell you about a project I did where I was building some chatbots, and it turned out that the human evaluation was kind of the hardest part of the project. So I was trying to build these chatbots for the persona chat dataset, and in particular investigating controllability. So we're trying to control aspects of the generated text, such as whether you repeat yourself, how generic you are, kind of these same problems that we noted before. So we built these models that control, the specificity of what we're saying and how related what we're saying is to what the user said. So here you can see that, our partner said something like, yes, I'm studying law at the moment, and we can kind of turn this control knob that makes us say something very generic like, oh, and then like 20 dots, or something just completely bonkers that's just all the rare words you know. And there's like a sweet spot between where you say, that sounds like a lot of fun, how long have you been studying? And then similarly, we have a knob we can turn to determine how semantically related what we say is to what they said. So, that's kind of interesting. It's a way to control the output of the NLG system. But actually, I want to tell you about how the human evaluation was so difficult. So we had these systems that we wanted to generate using human eval. So the question is, how do you ask for the human quality judgments here? You can ask kind of simple overall quality questions, like, how well did this conversation go? Was this user engaging? Or maybe comparative. Which of these users gave a best response? Questions like this. And we tried a lot of them, but there were just major problems with all of them. Like, these questions are necessarily very subjective. And also, the different respondents have different expectations, and this affects their judgments. So for example, if you ask, do you think this user is a human or a bot? Then, well, that depends entirely on this respondent's knowledge of bots or opinion of bots and what they think they can do. Another example is you'd have kind of catastrophic misunderstanding of the question. So for example, if we asked, was this chatbot engaging? Then someone responded saying, yep, it was engaging because it always wrote back, which clearly isn't what we meant. We meant, like, are they an engaging conversation partner? But they took a very literal assumption of what engaging means. So the problem here is that overall quality depends on many underlying factors, and it's pretty hard to kind of find a single overall question that captures just overall quality. So what we ended up doing is we ended up breaking this down into lots more kind of factors of quality. So the way we saw it is that you have maybe these kind of overall measures of quality of the chatbot, such as how engaging was it, how enjoyable was it to talk to, and kind of maybe how convincing was it that it was human. And then below those, we kind of broke down into these more low-level components of quality, such as, you know, were you interesting? Were you showing that you were listening? Were you asking enough questions, and so on? And then below that, we had these kind of controllable attributes, which were the knobs that we were turning. And then the goal was to figure out how these things affected the output. So let's see. So we had a bunch of findings here, and I think, like, maybe the ones which I will highlight were these two kind of in the middle. So the overall metric engagingness, which means enjoyment, that was really easy to maximize, it turned out. Our bots managed to get kind of near human performance in terms of engagingness. But the overall metric humanness, that is the kind of Turing test metric, that was not at all easy to maximize. All of our bots were way, way below humans in terms of humanness, right? So we were not at all convincing at being human. And this is kind of interesting, right? Like, we were as enjoyable to talk to as humans, but we were clearly not human, right? So, like, humanness is not the same thing as conversational quality. And one of the interesting things we found in this study, where we not only evaluated our chatbots, we also actually got humans to evaluate each other, was that humans are suboptimal conversationalists. They scored pretty poorly on interestingness, fluency, listening. They didn't ask each other enough questions. And this is kind of the reason why we managed to, like, approach human performance in kind of enjoyableness to talk to, because we just, for example, turned up the question asking knob, asked more questions, and people responded really well to that because people like talking about themselves. So yeah, I think this is kind of interesting, right? Because it shows that there's no obvious just one question to ask, right? Because if we'd assumed, oh, the one question to ask is clearly engagingness or it's clearly humanness, then we would have got completely different reads on how well we were doing, right? Whereas asking these multiple questions kind of gives you more of an overview. I am going to skip this just because there's not a lot of time. Okay, so here's the final section. And this is my kind of wrap-up thoughts on NLG research, the current trends, and where we're going in the future. So here's kind of 3 exciting current trends that I identified in NLG. And of course, your mileage may vary. You might think that other things are more interesting. So the ones which I was thinking about are, firstly, incorporating discrete latent variables into NLG. You should go check out the slides that I skipped over because there were some examples of this. But the idea is that with some tasks, such as, for example, storytelling or task-oriented dialogue where you're trying to actually get something done, you probably want a more kind of concrete, hard notion of the things that you're talking about, like, you know, entities and people and events and negotiation and so on. So there's some interesting work kind of modeling these discrete latent variables inside these continuous NLG methods. The second one is alternatives to strict left to right generation. And I'm really sorry I skipped over so many things. So there's some interesting work recently in trying to generate text in ways other than left to right. So for example, there's some kind of parallel generation stuff, or maybe writing something and iteratively refining it. There's also the idea of kind of top-down generation for especially longer pieces of text, like maybe try to decide the content of each of the sentences separately before writing the words. And then a third one is like alternatives to maximum likelihood training with teacher forcing. So as a reminder, maximum likelihood training with teacher forcing is just the standard method of training a language model that we've been telling you about in the class so far. So, you know, there's some interesting work on looking at more kind of holistic sentence level rather than word level objectives. So unfortunately, I ran out of time with this slide and I didn't have time to put the references in, but I will put the references in later and it will be on the course website, so you can go check them out later. Okay, so as a kind of overview, NLG research, where are we and where are we going? So my metaphor is I think that about 5 years ago, NLP and deep learning research was a kind of a wild west, right? Like everything was new and we were unsure, NLP researchers were unsure kind of what the new research landscape was because, neural methods kind of changed machine translation a lot, and it looked like they might change other areas, but it was uncertain how much. But these days, 5 years later, it's a lot less wild, I'd say. Things have settled down a lot. Kind of standard practices have emerged, and sure, there's still a lot of things changing, but there's more people in the community. There's more standard practices. We have things like TensorFlow and PyTorch, so we don't have to take our gradients anymore. So I'd say things are a lot less wild now, but I would say NLG does seem to be one of the wildest parts remaining. And part of the reasons for that is because of the lack of evaluation metrics that makes it so difficult to tell what we're doing. It's quite difficult to identify what are the main methods that are working when we don't have any metrics that can clearly tell us what's going on. So another thing that I'm really glad to see is that the neural NLG community is rapidly expanding. So in the early years, people were mostly transferring successful NMT methods to various NLG tasks. But now I'm seeing increasingly more inventive NLG techniques emerging, which are specific to the non-NMT generation settings. And again, I urge you to go back and look at the slides that I skipped. So I'm also seeing there's increasingly more kind of neural NLG workshops and competitions, especially focusing on open-ended NLG, like those tasks that we know are not well suited by the automatic metrics that work for NMT. So there's a neural generation workshop, a storytelling workshop, and various challenges as well, where people enter their, for example, conversational dialogue agents to be evaluated against each other. So I think that these different kind of community organizing workshops and competitions are really doing a great job to kind of organize the community, increase reproducibility, and standardize evaluation. So this is great, but I'd say the biggest roadblock for progress is definitely still evaluation. Okay, so the last thing I want to share with you is 8 things that I've learned from working in NLG. So the first one is, the more open-ended the task, the harder everything becomes. Evaluation becomes harder, defining what you're doing becomes harder, telling when you're doing a good job becomes harder. So for this reason, constraints can sometimes make things more welcome. So if you decide to constrain your task, then sometimes it's easier to complete it. The next one is, aiming for a specific improvement can often be more manageable than aiming to improve overall generation quality. So for example, if you decide that you want to, increase diversity of your model, like say more interesting things, that's an easier thing to achieve and measure than just saying we want to do overall generation quality because of the evaluation problem. The next one is, if you're using a language model to do NLG, then improving the language model, that is getting better perplexity, will give you probably better generation quality because you've got a stronger language model. But it's not the only way to improve generation quality. As we talked about before, there's also other components that can affect generation apart from just the language model. And that's part of the problem, is that that's not in the training objective. My next tip is that you should look at your output a lot. Partially because you don't have any single metric that can tell you what's going on, it's pretty important to look at your output a lot to form your own opinions. It can be time-consuming, but it's probably worth doing. I ended up talking to these chatbots a huge amount during the time that I was working on the project. Okay, almost done. So 5, you need an automatic metric even if it's perfect. So I know that you already know this because we wrote it all over the project instructions, but I'd probably amend that to maybe you need several automatic metrics. I talked earlier about how you might track multiple things to get an overall picture of what's going on. I'd say the more open-ended your NLG task is, the more likely you need probably several metrics. If you do human eval, you want to make the questions as focused as possible. So as I found out the hard way, if you define the question as a very kind of overall vague thing, then you're just opening yourself up to the respondents kind of misunderstanding you. And if they're doing that, then it's actually not their fault, it's your fault. And you need to change your questions. And that's what I learned. The next thing is, reproducibility is a huge problem in today's NLP and deep learning in general. And the problem is only bigger in NLG. I guess it's another way that it's still a Wild West. So I'd say that it would be really great if everybody could publicly release all of their generated output when they write NLG papers. I think this is a great practice because if you release your generated output, then if someone later, let's say, comes up with a great automatic metric, then they can just grab your generated output and then compute the metric on that. Whereas if you never released your output, all you released was some kind of imperfect metric number, then future researchers have nothing to compare against. So lastly, my last thought about working in NLG is that it can be very frustrating sometimes because things can be difficult and it's hard to know when you're making progress. But the upside is that it can also be very funny. So this is my last slide. Here are some bizarre conversations that I've had with my chatbot. Thanks. All right, thanks.